Now in this lesson, we're going to talk about limits. Starting with this function, f of x equal to x squared. Suppose I asked you to find f of 1. We can do that by replacing x by 1 in the given expression, which yields to 1 squared equal to 1, or graphically, by starting at x equals to 1 and project to the curve parallel to the y-axis in order to read the corresponding value of y, which in this case is y equal to 1. Now looking at this curve, f of x equal to 1 over x minus 1. Suppose I ask you to do exactly the same thing. Find f of 1. Now replacing x by 1 in this function would yield 1 over 0. 1 over 0, which is undefined. And graphically, we can see the restricted value x equal to 1 by looking at the vertical asymptote that we have at x equals to 1. However, even though we cannot really evaluate f of 1 or find an image for x equals to 1 by f, we can still study the behavior of the function around x equals to 1. So in order to do that, instead of setting x exactly equal to 1, what we can do is approach 1. So by approaching 1, we can either be approaching 1 from the left or from the right. So let's just start by approaching 1 from the left side. Starting randomly at a random value of x on the left side of x equals to 1, which in this case I took x equals to 0. So starting at x equals to 0 and evaluating f of x for x equals to 0, we find f of 0 to be equal to negative 1. Now let's just start approaching x equals to 1 by taking a second random point, 0.5 for example. F of 0.5 yields a y value of negative 2. Let's move even closer. F of 0.75 is negative 4. And then I'd notice as I move further towards x equals to 1, we'd notice that the values of y are in fact dropping further towards negative infinity. As we can see in the table here, x equal to 0.99999 had a y value equal to negative 10,000, while the value right before it, 0.999, had a y value of negative 1,000. So the pattern for the values of y we see here tells me that y is in fact dropping further towards negative infinity as x approaches 1. Now that is denoted by taking lim for limit, f of x, limit of f of x, because f of x is the function that we're finding the limit to at x equals to 1. And then we need to indicate the value that x is approaching. Now over here we can see the arrow indicating that x is not really equal to 1, it's approaching 1, and that negative at the exponent of 1 indicates that we're approaching x from the left. So we need to be specific on whether we're approaching x from the left or from the right, because they can be two different limits. So when x is approaching 1 to the negative, which means x is approaching 1 from the left. Now the output of the limit gives the value that y approaches as x is approaching its value, which in this case, to the left side of 1, y was approaching negative infinity. So in that case, the limit of f of x when x is approaching 1 from the left is equal to negative infinity. Now the same way I approached 1 from the left, I could have approached 1 from the right. So doing that, now let's just approach 1 from the right side. Now we can see here that I started randomly at x equals to 2 because 2 is on the right side of 1, and then I started to approach x equal to 1 from the right side by taking these different values of x as I approach 1, I find the values of y, I notice that the value of y, as I keep getting closer to 1 by x, the value of y is in fact growing infinitely large towards positive infinity. And similarly to how we denoted the limit to left, I now denote the limit to right. So we have the limit of f of x as x is approaching 1 plus is in fact equal to positive infinity. So remember, the outcome of the limit is the value that y approaches as x approaches its indicated values. Now comparing the limit to left and the limit to right, we notice that these two limits are different. So 1 does not have the same limit to its left and to its right. So when that happens, we say that the limit of f of x when x approaches 1 does not exist. So for the limit at x equals to 1 to exist, the function must have the same limit to its left and to its right, which in this case we don't have that. So when the limit to left and the limit to right are different, we say that the limit at that point of the function doesn't exist. However, for some functions, we could possibly have the limit to left and the limit to right being equal. And when that happens, in that case, the limit of the function at that point would exist and would be equal to its limits to left and right. Now, up till now, we have seen how we can find the limit of a function at a given point by approaching that point from its left and from its right, and then compare these two limits. However, looking at the curve we have here, let's just reset everything here. The reason we found the limit of f of x at x equals to 1 was because x equals to 1 is a restricted value for the function. We can see by looking at the graph that this function does not have any other restricted values. So for any point other than x equals to 1, we could just find the image of that value of x by just replacing it within the function. For example, for x equals to 2, I can find its image simply by replacing x by 2 and finding f of 2. But that was something we could not do for x equals to 1 being a restricted value, and this is why we had to refer to limits. However, there's another pair of limits other than the limit to left and right that we have to find, which are the limits at the infinite bounds. Because f of negative infinity, for example, can not be evaluated using the equation of the function. Yet, we still need to find the behavior of the function at x equals to negative infinity. So, using a similar approach, because I cannot find f of negative infinity, what I would do is approach x towards negative infinity. So over here, approaching x or taking x towards negative infinity and using a table of values the same way we did for x equals to 1. So what I need to do here is start from x equals to negative 10, for example, and then start taking these values of x towards negative infinity by going towards negative 100, negative 1000, negative 10,000, etc. So looking at the y values, we notice that the y values are becoming infinitely small. And by infinitely small, we mean that they're in fact approaching 0. So over here, we get to deduce that the limit of f of x when x is approaching negative infinity is in fact equal to 0, because as x goes further towards negative infinity, y is further approaching 0. And we can use a similar approach to find the limit when x is approaching positive infinity of f of x, which would eventually yield to y approaching 0 as well. So for this function, the limit when x is approaching negative infinity and when x is approaching positive infinity of f of x in both cases is in fact equal to 0. And we can see graphically that at both infinities that the function keeps on dropping and getting closer to y equals to 0, to the x-axis, as we move further towards the left or to the right, towards positive infinity and negative infinity. So that was the introduction to limits. Now in the next lesson, we're going to look at evaluating limits graphically or algebraically using the given expression for the function.